Hey class, Bob Greavy here. I'm going to walk you through a simple transportation problem. Um, Transportation problem is a problem where we have multiple what we'll call origins, and I'll indicate those origins with these circles or nodes. So we have multiple locations basically from which we perhaps transport goods. So these circles might represent warehouses from which goods are shipped to stores, or they might represent factories and goods are shipped from those factories. So the bottom line is there's some location from which products are shipped. And then we have also destination nodes. So you have origins and destinations. And in this example, we happen to have 3 origins and 3 destinations. You could just as easily have, any number of origins and any number of destinations. And then along with each origin, you'll have a capacity. So every single origin has some number of units of a product that they can deliver, that they can produce and ship. So let's say this first node here can ship 100 units, the second node can ship 200 units, and the third can ship 300 units of product. So we have a total capacity from our origins of 600. And let's say that each destination has a need or a demand of 200. Just keep it simple. So the challenge becomes, what's the most efficient, cost-effective way to get these 600 products from these 3 origins to those 3 destinations? What's the most efficient in terms of costs? So you kind of think of these left-hand side as capacity constraints or supply constraints, and then we have constraints on the right-hand side that indicate a demand constraint. We have to get that much product. And then let's label these nodes. Let's label these nodes 1, 2, 3, and 1, 2, 3. And then um, each potential route or each potential um, ability to ship units from a particular node to a particular node, we'll represent that with an arrow. Okay, so I can ship from 1 to 1, I can ship from origin 1 to destination 2, and I can ship from origin 1 to destination 3. Similarly, I can ship from origin 2 to 1, origin 2 to 2, origin 2 to 3, and so on and so forth. Now, it might be that some of these routes are impossible. Perhaps it's impossible to ship from route, or rather from node 3 to destination 3. And if so, you just wouldn't have an arrow there. Let's go ahead and include one. Now, on each arc, each arrow, in other words, you'll have a cost associated with that transportation, and it's a per unit cost. So let's say it costs $3 to ship 1 unit from node 1 to node 1. So maybe this node 1 on the left represents Oklahoma City, the node 1 on the right represents Tulsa, and it costs us $3 to ship 1 unit from Oklahoma City to Tulsa. How much money would it cost us to ship 3 units from Oklahoma City to Tulsa? Guess what? $3. So we just keep it that simple. And then we'll have costs associated with each of these. 2, 2, 3. So I'm kind of making up a problem to solve as we go here. But so now you have a typical transportation problem. The goal is figuring out what's the best way to get these 600 units to these 3 destinations. This is a linear programming problem, and it's a minimization problem. The goal here is to minimize the total transportation costs, subject to what will wind up being 6 different constraints. You have some constraints. The first constraint says that you can only ship 100 units out of node 1. You can only ship 200 units out of node 2, and you can only ship 300 units out of node 3. You also have 3 demand constraints that say, listen, 200 units have to arrive over here at node 1, 200 units have to arrive over here at node 2, and 200 units have to arrive at node 3. So we have a constraint for every single node, and we're going to have a decision variable actually for every single arc. So we're going to say we want to let x, I, j correspond to, represent, or I'll just write an equal sign here, equal the number of, I'm going to abbreviate number, the number of units shipped from node I to node J. Okay, so I'm about to erase this to make room for the formulation here. So go ahead and write this out if you haven't already. And when I'm going to pause the video, and when I come back, you'll see some white space for me to formulate this. So you're going to need this picture on your own page here shortly. Okay, we're back. Instead of erasing it, I just drew it really small so I'd have some more room here. The goal of our objective function is to minimize my total transportation costs. Let's see. So how do I write total transportation costs? Well, it's going to cost me $3 for every single unit I ship from origin 1 to destination 1. And the number of units I ship from origin 1 to destination 1 is represented by the decision variable x11, as we've indicated at the top here. So in this case, the I is the 1, the J is the one on the right, the I is the node on the left. And let's say if x11 equals 10, what I'm saying is I'm going to ship 10 units from origin 1 to destination 1. And therefore 3 times 10 will be $30. So this 3x11, it's not 3x11, by the way. That's a mistake. People see that and think that. This 3x11 represents the total amount of money I'm gonna spend shipping units from node 1 to node 1, from origin 1 to destination 1. Similarly, when I add 2x12, 2x12 is the amount of money I'm going to spend shipping units from node 1 to node 2. And so it goes. I'm going to write the rest of these expenses. 4x12. You might pause the video, see if you can complete this objective function. That should be a 3. Whoops. 4x13 from node 1 to node 3. Plus 2x21 plus 2x22 plus 3. I'm looking at this 3 right here. I shouldn't have circled that. That's going to confuse people. Let's see if I can put that back to normal. 3x23. Okay. This was originally a 1 before I accidentally deleted it. Plus 1x31 plus 2x32 plus 3x33. So when you add all of these up, you get the total amount of money you're going to spend shipping. So this entire thing right here is my objective function, and I want to keep that as small as possible. And you see I have 9 decision variables, and I want to figure out what's the optimal amount to ship for each of these potential scenarios, each of these 9 decision variables. Now I've got those 6 constraints. You're going to see they're relatively easy once you understand the decision variables meaning. Again, Xij is the number of units shipped from node 1 to node J. I think you'll agree with me that I can't ship more than 100 units from node 1. That's how much capacity I have. So we can say that x11 plus x12 plus x13. I'm going to pause right there. You might want to pause as well, but look at that and tell me what that is. When you add up x11 plus x12 plus x13, think, what is that? That's the total amount I'm going to ship from node 1. Okay, there's only 3 different things or ways I ship from node 1, and that represents every one of them. And that total shipped from node 1 has to be less than or equal to 100. And you'll have similar constraints for node 2 and node 3. You might pause here and see if you can fill in the next two constraints. Okay, x to 1 plus x to 2 plus x to 3, and it has to be less than or equal to 200, the capacity of node 2. Similarly, x 3 1 plus x 3 2 plus x 3 3 must be less than or equal to 300. Okay, so there you have your three different what I call capacity constraints or supply constraints. Can't ship more than is available. Then we also have to have constraints that ensure that the product gets there. Because right now, if we solve this, if we optimize this right now, what it would do is it just wouldn't ship anything. Because the cheapest thing to do would be just to ship 0, and then we wouldn't have any cost. So we need constraints that impose this rule that says 200 units have to arrive at each of the 3 destinations. So we'll have these demand constraints. So I'm going to write something. I want you to pause and think about what it is. The first thing I'm going to write is x 1 1 plus x 2 1 plus x 3 1. Now is when you pause. What is that? Welcome back. That is the total amount of product shipped to destination 1. There's 3 ways that product gets there, from node 1, node 2, and node 3. And you add those up, and that's the total amount of product that's going to arrive at node 1 on the right-hand side. And that has to be at least, you could say greater than, or you could just make it equal to, let's say greater than or equal to 200. Now, it's always going to be equal to, when we get the final optimal solution, the left-hand side is going to equal 200 because we're minimizing a cost, and it's never cheaper to ship more product. So this left-hand side of this constraint will add up to 200 after it's optimized. I'm going to do the similar constraint. You may want to pause and do the same thing, but I'm going to do similar constraints for the destination nodes 2 and 3. X 1 2 plus x 2 2 plus x 3 2 must be greater than or equal to 200, and x 1 3 plus x 2 3 plus x 3 3 must be greater than or equal to 200. So there you go. You have just formulated a transportation problem in which we have minimized, or we're going to ask the computer to minimize the total transportation costs, subject to the 6 constraints outlined there. These first 3 constraints ensure that we don't ship more than we have. These last 3 constraints ensure that we get at least as much product as we need. So if we plug that into Excel, and I encourage you to do that, you'll find out the optimal way to get products from those 3 origins to those 3 destinations. Now, if you're like me, you're thinking that's incredibly simple, and in real life it gets more complicated, and that's true, but this is the type of thing that can be done in order for, let's say, FedEx to figure out the most economical way to get those hundreds of thousands of packages from those thousands of origins to those thousands of destinations on a daily basis. This is the same type of optimization that can be done in that environment. So that's all for this video. I'm going to come back with an assignment one.